Hello everybody, hope you're well. I think this is working. I'm not totally sure. I guess we'll find out. It says it's live. I can't see the preview. But yeah, so it's Dr. D. It's been a while. I'm at a conference in Charleston, and I wanted to talk to you guys about the project. So we'll just give it a go and see how it goes. We're going to talk about part 2. Right now, we'll start with people boxes with retirement. I know people were struggling a little bit. So we've got some census data here. You can see we've got 280 cities all the way from row 3 to row 282. And then we've got a number of things you can see in this up here in the formula bar. The implications of the variables, whatever the variable descriptions. And yours might not look like this. You can see that you can click and drag here to change the length of it. I could probably leave it short, but there you go. So just to get started, I want to look at this retirement. You can see that we've got a few questions. The first, does income vary with retirement? For this, define retirees as people age 65 and up, and find the proportion of each city that is retirees. So that's the first thing we have to do. We're going to have to figure out for each city, how many of them are retirees. It says then split the data into 2 groups. So we're going to split it just through the middle once we've sorted it. We're going to test to see if there's a difference in household income between the MSAs with the most and least retirees per capita. And then if we look down later, we can see proportions of citizens between old cities and other cities. Use the 2 groups over here. Use these 2 groups, pardon me. Test the difference across the 2 groups. So we've got a lot of different differences here. So we'll take a look. First thing we have to do is we have to find retirees. So you can see that here this column O is male 65 and up, and this column, let's see, where is it? P is female 65 and up. And then over here we've got column L is total. So column O, I said P, but it's not P, it's O, R, and L are the 3 that are going to matter. I'm just going to move over here. I'm going to create a new variable called %retired. That's going to be equal O3 plus, let's do parentheses, O3 plus R3 divided by L3. And so for Abilene, Texas, we should see that we got 12% of the population are retired. To double check, again, O is male 65 and up, R is female 65 and up, and L is total population. So this is the proportion of the total population that's retired. Went the wrong way there. We want to go down here. So I'm just filling down everything here. To do that, I go left, control down, right, control shift up, control shift down, control D. Just pulls that whole thing down. And you can see that what we now have is for each city, the proportion of the city that is retired. The rest asks me, just that was control shift left, control shift down. Next, we want to sort the data. You can go to data sort. I always use the Alt-DS, which is the keyboard shortcuts to sort. And as long as this is checked here, this is my data as headers. See what that does. It allows us to use our built-in headers. %retired is the variable I just created. So I'm going to click OK. And if I did it right, we should see that the city with the fewest smallest proportion of retirees has 5%. All the way down to the bottom here, which is 35%, so 7 times is the order of magnitude there. Anchorage, Alaska does not have a lot of retirees, and then a number of these are also college cities. Atlanta, Georgia, where I live, is pretty low. And then Punta Gorda, Florida is the retirement capital of the country. So, and you can see Florida, you know, a lot of retirement communities in Florida. It's taking care of that. So back to the brief, what we just did here was we split the data, we found the proportion that's retirees. If we want to split the data into 2 groups, you can see that we've got, down here, we've got 280 cities. So that's going to be 140, 140. To split that down the middle, we're at row 3. If we go to row 142, you can see now we've got a count of 140 cities. So Abilene, Texas, Orlando, Florida. Orlando is part of the older cities, Abilene is part of the younger cities, and that's where we're going to draw the split. This says test to see if there's a difference in household income between the MSAs with the most and the least retirees per capita. So let's just call this, let's see, let's work over here. We're on part 2. Let's call this 2A, income. And this is going to be a test of two means. So if we want to do step 1 here, we're going to need a null. We're going to need an alternative. The null is going to be that mu1 minus mu2 equals 0, right? Because it says right here, it says test to see if there's a difference. And if there's a difference, that's going to be right here, not equal to 0. And so that's the equal, not equal. Step 2, we need to choose some level of significance. We'll stick with 0.05. That should be fine. It's going to make it small there. There we go. Step 3 is to choose a test statistic. I'm not going to type it here. But we've got a difference in two means. There's no reason to think that we have the population standard deviation. So we're going to use a t-statistic that has well, maybe I'll write it for you so that you can see it. So let's see, we've got this here. I don't have my tablet with me where I can draw, so I'll just try to do the best I can with the mouse. Let's see. So this is going to be brushes. There we go. T equals, it's going to be x bar 1 minus x bar 2. And I know this is not ideal, but I'm in a hotel room in Charleston, and this is not plan A for anybody. Nonetheless, I hope you find this useful. There you go. X bar 1 minus x bar 2 minus d0, and then the denominator, square root. And then here we've got s1 squared over n1 plus s2 squared over n2, and that's the variance of the difference in two sample means. Under the null, this has a t-distribution with the degrees of freedom that's not super pretty, but we'll pull up the degrees of freedom when we need to. So I'll just put a dot in there. We're going to fill that in eventually. So right now, what we want to do is we want to come up with this t-statistic. So to do that, you can see we're going to need a few things. We're going to need x bar 1, x bar 2, n1. This is step 4, by the way, when we're actually collecting the data. N2, S1, S2. And to do this, to calculate these, if you recall, I wrote it right up here. We're looking at income. X bar 1 is going to be the average, the sample mean income for our younger half of our sample. So right here, let's see, where's income? Median household income. That's the one we're going to use. Column J there has median household income, and that's the one we're gonna deal with. So let's pull that in here. Median household income, the average of that. So that was column J. So we're going to use J3 colon J142 because that will take that first half of that column, and you can see that's the average, 39,856. And then we're going to do average of J143 to J282. And for the older half, it's 38,059.56. For N1, we're going to use count. And we can use the same J3, J142. And then equals count J3, J2, or not J143, J282. And then here we've got equals stdev.s, J3, J142. stdev.s J143 colon J282. And so now we've got a bunch of numbers that we can use to calculate our t-statistic. To do this, we're going to calculate our, we also need d0. d0 always comes, that's the difference under the null, and we articulate whenever we state our hypothesis, so that's there. All right, now we're ready to create the numerator for our t-statistic. That's going to be x bar 1 minus x bar 2 minus d0, and you can see that I'm just using these values right here. That's where those are coming from. So I'm just pulling this information right here, and then I'm calculating it using Excel as my calculator. So that's our t numerator. We're going to need a t denominator. To do that, actually, I want to calculate these first. So we get s1 squared over n1, s2 squared over n2. If we add those two together, we'll get the variance. So right now we're going to try to calculate this thing here. We're going to do these two parts first. So s1 squared over n1, this squared divided by n1, and then since it's a formula, it should be the case that when I calculated it, let's see if that worked. Yep. So that right there, you can see, just shifted these down. The variance of these is the sum, or the variance of x bar 1 minus x bar 2 is the sum of these, and our t denominator, which is the standard error, is just the square root of the variance. And that gives us the things we need to calculate our t statistic. T numerator divided by t denominator. You can see we get a t statistic of 2.28, or thereabouts. And so that's the end of step 4. We've calculated our t statistic. And so if this is just noise, then it looks like we have a t-score of 2.28, assuming the null is correct. Now, what we need to do is to convert that into a p-value, so we can try to draw a conclusion about the validity of the null. To do that, we're going to need to calculate our degrees of freedom, and that's going to take some doing. So the reason it'll take some doing is that the degrees of freedom formula it's not simple per se. So our degrees of freedom in this circumstance, and again, I'm doing this in mouse, so bear with me. Nobody's idea of plan A. S1 squared, which is the sample variance for sample 1, over n1, plus S2 squared over n2, and that is squared. And so that is that variance squared divided by, and then this has sort of a left side and a right side. So 1 over n1 minus 1 times, there we go, S1 squared over n1, that quantity squared, that's the left side, plus 1 over n2 minus 1 times S2 squared over n2, the quantity squared. And it looks kind of hairy, not going to lie. But I do want to draw your attention to the fact, as we've discussed, we've got these fractions already calculated. In fact, we already calculated this sum. That's this right here. So those two things are already calculated. Similarly, we already have this fraction calculated, and this one as well. So when we actually calculate these degrees of freedom, they'll be much more straightforward. So the first thing to do, we want to calculate that numerator. And so that's this variance squared, because that variance is already this sum. So we've already got that. And you can see, puts us in the realm of scientific notation. That's okay. We should expect, by the way, our degrees of freedom should come somewhere down into the order of magnitude. Hey, take out the trash. Probably not going to do that. I'm far away from home. Should come somewhere within the order of magnitude of our sample sizes. So we're going to be looking at hundreds of degrees of freedom, not thousands, and certainly not, tens of millions. That's our df numerator, degrees of freedom numerator. We're going to have df denominator, and I have df denominator L, which means right now I'm looking at this left part. So to do that, actually, we can do equals 1 divided by, and then I've got this n1 minus 1 times, and then I've got this s1 squared over n1 squared. Not y, there we go, that's what I want. And so you can see that's the left side here. And then if I do df denom right, it should be the same. Yeah, it still refers to those two, which gives me my df denominator, which is just the sum of these two, right? So I did this just to draw your attention. I did this on the left side with n1 and s1 squared over n1, and then I did on the right side, and now I'm just summing those two. You can use the sum formula if you want with only two numbers. It's a little faster to do it by hand, but you can see I'm just adding those two together. Now, if I take my df to numerator, I already have this cell here. If I take my df to numerator divided by my df denominator, I should find that I have 252 degrees of freedom. Remember, with degrees of freedom, we're always going to round down. I'm not actually going to round in this case because Excel knows how to interpret it, but if you had a table, we have 252 degrees of freedom, which again, it's not the same as these, but it's not the same as this sum, but it's within the same order of magnitude. So once I know that, now I need to know how to calculate the p-value.